Hello everyone, so I'm Amir, I'm a doctoral student in ETH Zurich, and I'm here to present this talk on aligning sequences using seed sketches. So this is just like the overview of the method, and it's to, the core idea that we want to present here is that instead of using seed and extend, standard seed and extend for doing sequence to graph alignment, we can rely on sketches that are essentially a map from the sequence space to a vector space, and then we do some nearest neighbor querying on that vector space instead. So then you can potentially find things that are not exactly matching but are similar. So this is the overall idea that we want to present. Now, let's formalize a bit to what the sequence, like the graph model is. So given some integer k and some sequence set s, this is a de Bruijn graph which encodes the sequence content in its vertices and edges. And nodes are just the k-mers in the sequence, and the edges are like a traversal of these edges, and they encode, and each edge is also associated with some label which encodes your sequence content. Now, if you have a walk is defined as a set of adjacent edges, and you can define also a spell of a walk as all the sequence content on that walk. And you can, for example, see here the example. Oops. You can see here that for this walk, you have one k-mer and then two edges, and then you concatenate them, and that's the spell of the walk. And now you can define, finally, formalize the sequence to graph alignment is defined as, given a query, you want to find the closest spell to that query using by some traversal of the graph. Now you can see that a standard approach to like solve this problem would be a dynamic program where you start the alignment from different nodes in the graph, and you try to account for different edit operations that you apply to this graph, and like find the optimal alignment. The problem there is that doing so would induce some kind of a linear cost with respect to the graph size for your alignment time. Now, this is obviously not optimal if you have if you're dealing with a really big graph. Now, again, a standard way to get around the problem is that is the seed and extend approach, where instead of starting alignment from every node in the graph, you would only start alignment from a seed, which is defined as a match wherever there's a match between k-mer in the query and nodes in the graph. Now, so this is obviously desirable because that's a fraction of the nodes in the entire graph. However, the problem is that if you're dealing with something with potentially high variation, then you might not have any matches at all. So, like you can imagine if you have a mutation every kth base pair, that means that you don't get any matches between the query and the graph. Now, you might imagine that reducing the k might resolve this issue, but unfortunately, this is not like it might resolve one issue, but it might introduce others. For instance, like one problem is that reducing k might basically make your graph like a hairball because everything would be connected, or it becomes like a complete de Bruijn graph. And the second thing, which is actually maybe more connected to the theme of the talks at the conference, is if you, for example, looking for repeated regions, and if it's important to, for example, know the copy numbers, k should not be shorter than the length of the repeated region, because otherwise you lose sight of how many times that repeated region occurred. So these are all the arguments that you would not, you don't want to reduce k too much, because it introduces some other problems. And that's exactly the motivation for our approach, which is relying on long seed sketches as opposed to potentially shorter seeds. Now, without actually discussing what the sketching exactly is, conceptually you can think that it's basically a mapping from the sequence space to a vector space, in that it preserves the maybe edit distance and like L2 norm, L2 distances between the sequences. So in this illustration, for example, you have some nodes in the graph that are highlighted in green, and they're represented in this two-dimensional illustration. And then you have, for example, some node in some k-mer in the query. So CTG is now, even though it's not equal to CTA here, you see. So even though these two are not matching, but they're proximate, so they're close to each other. So that's how we can now make a nearest neighbor query for that CTG, and then find the closest node, and then start doing backward and forward alignment there. So this is how like the overall method works. However, you can see that like doing this, like vectors, they have a lot of advantages, but they introduce a very significant problem, which is the curse of dimensionality. So curse of dimensionality, I can make it like an intuitive example here. So imagine like if people in the audience now like wanted to find the closest person sitting near to them. So they obviously would look around them. So you have like, 4 seats maybe, like forward, backward, like right and left. So that's not, maybe so hard. But imagine if you were sitting in 3 dimensions, like then you had to look in 8 different directions. And now if you were 4 or 5, dimension, that would basically exponentially explode. And finding nearest neighbors becomes a very, very non-trivial problem. And so here, for the sketches, we actually have to use higher dimension to get good accuracy, which means we're dealing with, like 100, potentially, many, many dimensions. And doing nearest neighbor queries is a very non-trivial task. So fortunately, this was the method that turned out to be, to give us the optimal time accuracy trade-off, which is a hierarchical index, more specifically HNSW index, which essentially it has many layers, and it starts from very like crude or non-granular level. And as you go, so you start querying from the top level with very few nodes, and as you go lower, you refine the answer to your query, your nearest neighbor query, and at the very bottom you end up with something quite accurate. Now, and then this is what we use for getting the optimal time accuracy trade-off, and also it actually scales really well to billion scale. That is like really what we want to operate on in bioinformatics. Now, so far we only saw like a black box what sketching is, but now we can go a little bit like white box and look inside it. So it can be described in 2 main steps. First, conceptually, it can be seen as a tensor embedding, and the sketching is an approximation to that. Tensor embedding is essentially taking a sequence and spitting out a tensor, which is of 10 dimension, 10 being a parameter of the model. And every element of this tensor is counting its occurrences of a subsequence in X. Now here, let me emphasize that subsequence is not contiguous, so it can have many gaps. And for example, in this example, X, you can see the row A and column C. So these two, they correspond to, like 2 occurrences. So there's one A appearing before C here, and then one appearing before C here. So the second one is not contiguous, which is the reason that it has a high tolerance to indels. And that's like, that what we want the method to have. Now, if you do this for 2 different sequences, so you have X and Y, and if you compute the edit distance, you can intuitively see that, for example, this deletion of A from X to Y has zeroed out the first row of tensor Y. So here, and that's why in the difference tensor you see that it's a positive value there. And you can make like similar observation about the insertion of T and substitution. And this is the intuitive explanation for why this tensor embedding is a good idea. However, these tensors could be potentially huge because if T is large, that could be exponential. And that's why we have the tensor sketching instead. So the first important property it has is that it's a linear projection from the tensor dimension to a constant D dimension. And importantly, it preserves the L2 norm. So that's what we saw intuitively, that it preserves the edit distance. And in this case, we can now map it to a lower dimension, and it still preserves that approximately. The second property is that not only it's preserving these things well, but it can also be computed fast. So for instance, you can imagine that T could be large, or like even moderate values of T could be quite high dimension. Fortunately, we don't even have to construct these tensors because we can do this sketching implicitly. And here's an illustration for D1 dimension of why this is actually feasible. It's we call implicit sketching because we don't actually construct the ambient space. We just like, and the gist of the idea is that you can actually rewrite the sketch as a recursive sum of 2 terms, which means that you can now just append one character by another and end up with the sketch that you're interested in without having to ever construct the tensor. And that means that you have a linear time complexity to for computing these sketches. Now this is just like to take this to see how well it is to approximate the mutation rate. So mutation rate is simply the so you insert a substitution and indels at the different positions by chance, and then you compute the tensor embeds and their L2 distances, and this is what you get on the left plot, and that's the tensor embedding in the y-axis, mutation rate in the x-axis, And then you see that it rather nicely linearly preserves, so, or slightly, there's some quadratic part, but up to, like 50% mutation is still rather linearly preserving the mutation rate. And the other plot, that's the tensor sketching. And as you see, the bands are now more wide because this is an approximation to tensor embed. However, different bands correspond to different values of D. So like the most narrow bound is the 64 dimension. The widest band is 8 dimension. So that's, like the accuracy time, dimension accuracy trade-off that you get. But you can still see that you can distinguish pairs with, like 0.2 mutation from, random pairs. So which is a rather nice property. Like 25% mutation, you can still distinguish it from noise. Now, like putting everything together, this is the main experiment. Like this is the sequence to graph experiment. That on the x-axis you have mutation rate, and on the y-axis you have the recall. How many times you actually find out the correct result, and different traces correspond to different methods. So the main two ones here to be focused on is the metograph align or MG align and metograph sketch. So metograph align is the standard seed and extend. And metograph sketch is the same method with the augmentation that we changed the seeding scheme. So that's, you can make like a head-to-head comparison, and that's the pink and purple traces. And you can see there's a jump, in recall for the 15% on higher mutation rate. Now you could see that VG map and has a higher recall in this case. However, this is a very small graph. So if you increase the size from 100,000 to 10 million, or the largest one here is a 1 billion node graph, the VG actually runs out of memory, which was the 100 gigabyte capacity, hard limit that we considered. And in all three other experiments, actually, this metograph sketch is actually the one that achieves the highest recall. Now, to delve a little bit deeper to like what's the scaling here with respect to what's the growth rate. So the left plot here is the memory, is the peak memory usage of the method. And so it's a log-log plot. Y is the peak memory usage. X-axis is the number of nodes in the graph. And the dash trace shows the linear scaling. So basically, if something is parallel to that dash trace, it means that the method is peak memory. It scales linearly with respect to the graph size. So that's obviously a desirable thing if you're dealing with really big graphs. And the other plot, the one on the right, that shows the average alignment time per each query. And in this case, the dash trace shows the logarithmic scaling, so that being parallel to that dash trace is actually means that the average time for each query is logarithmic. So that's, again, that's a nice property. You want to, like your query time, alignment time to be, not growing too fast with the graph size. And so one thing to note here, the two traces for VG, actually they've stopped off because they, again, ran out of memory. So that's the largest thing we could run for those two VG traces. And there's another thing to note is that the gap between MG sketch and MG align, so that's the main two methods that, and then slowdown in the, for example, the alignment time, that's accounting for the additional Cs that we have. So obviously we have many more Cs to start extension, and that's why it's slower, because it takes more time to, extend those things. And the other one for the peak memory, that's that additional factor of 10 in memory usage is accounting for construction of the index. It's a very complicated thing to build, actually. So finally, let me make the concluding remarks. So I think it's very interesting that we can actually, so potentially we used K80 here, but we could have gone higher. It was a very implementation related reason we didn't go higher. And it's very interesting. We can actually essentially go as long as we want to define the seeds. And again, it would be interesting for for example, long reads that if you can tap into these very long reads that are potentially noisy or they have high variation, and this approach could actually realize their full potential. The second thing is for me, it's just interesting that to see that vector representations are potentially they can capture a lot of information in few dimensions, and that's as opposed to hash tables. That's a lot more information they can capture. However, again, Kersel dimensionality is an issue that when you go from k-mer matches to vectors, but it fortunately can be now avoided using both engineering and algorithmic developments. So this is now essentially you can call it a result issue. For this 1 billion scale that we experimented on, it was okay. And so we could also, think about potentially, like if you're working with vectors, there's a lot of hardware optimizations. Actually, a lab mate of mine, Ragnar, one of the co-authors, he wrote a CUDA version of the tensor sketch, which could sketch the human genome in roughly half a second with the, one GPU, with a high-end GPU. And also the FICE, the implementation we use for the nearest neighbor index, that has CUDA implementation. So working with vectors has some advantages when it comes to, like hardware optimizations. And I think one last thing that maybe I find very interesting for future direction is that even though I presented the whole work as a thing about randomized algorithms, so like it was a sketch as a randomized algorithm, but you can take it out and replace it with something differentiable, like some vector that you can optimize with, reinforcement learning, and potentially maybe propagate bit back. With if you've got a good alignment, you can change your representations. So, and then another direction that it's very interesting is, for example, retrieval enhanced inference on top of this thing. So basically, knowing that now we can scale up with this vectors, we can operate them at like very high scale. We can think of other ways of maybe fine tuning or representing sequences as vectors. And with that, I'd like to thank my collaborators in the biomedical lab, and I'll be happy to take any questions you may have.
That was great.